In this online lecture, we're going to discuss the relationship between the intensity of an absorption band and the type of bond that gives rise to it. Notice, again, looking at our chart here, the intensity of some of these absorption bands vary. You have strong, broad, you have medium intensity, all the way down to weak intensities. Why is it that some peaks are stronger than others? Well, it has to do with a concept that we learned before. Remember, there's an equation that we learned that says this right here, the dipole moment, and that is in this case the dipole moment of a bond, is equal to E, the charge on either one of the atoms in the bond. And remember, they're the same. One is positive, the other one is simply the negative of it. And we multiply it by D, the distance between the two atoms, or in this case, the length of the bond. Remember, what we learn is that the greater the charge on the atoms and the longer the bond, the greater the dipole moment. However, the new concept that we're learning here in this section is this point right here. The greater the dipole moment, the greater the change in dipole when a bond stretches. Think about it. This equation supports that truth. Dipole moment is equal to E times D. And if a bond stretches, the D value increases. That in turn increases dipole moment. This brings us to the second concept that we have to understand. Another relationship is this right here. The greater the change in dipole moment, the more intense the absorption band is on the IR spectrum. So let's notice this trend on the chart right here. For instance, let's look at the C double bonded to C bond. Notice its intensity is medium. But look at the C double bonded to O bond here. Its intensity is strong. Notice the C double bonded to O bond would have a greater dipole moment than the C doubly bonded to another C. Remember, oxygen is a lot more electronegative than carbon. Therefore, the C double bond O bond would be a lot more polar, or in other words, have a greater dipole moment. So, when we stick these functional groups in the IR and these bonds stretch, we would expect to see a stronger intensity signal for the C double bond O. In fact, let's look at it in the IR spectrum. What you see right here is a very characteristic C double bond O absorption band. Notice its strong intensity, as in it goes almost all the way down to the bottom of the chart. Compare that to, for instance, this absorption band right here. This doesn't even go halfway down the chart. This would be more on the medium-weak end for intensity. And this right here would be an extremely weak intensity. Notice this concept also explains another trend that we see on our wave number chart. Notice, compare the OH, NH, and CH bonds. The trend here is simply this. The CH bond would be the least polar, and the OH bond would be the most polar. Again, because remember, carbon and hydrogen roughly have the same electronegativity, and oxygen and hydrogen have the greatest difference in electronegativity. That means when you stick these bonds in the IR spectrum, you're going to have the CH bond having the smallest change in dipole moment as it stretches, and the OH bond having the greater change in dipole moment as it stretches. What we're learning here is the relative intensities. That means the CH bond would be less intense, and the OH bond would be more intense. And of course, the NH bond would be somewhere in the middle. Notice we see this in our wave number chart. Right here, we have the OH, CH, and NH bonds. Notice how the OH has the strongest intensity, and the CH and NH have medium intensities. So, what's it all about here? Key points. Number one, we saw the greater the dipole moment, the greater the change in dipole moment when a bond stretches. And that means number two, the greater the change in dipole moment, the more intense the absorption band is going to be on the IR spectrum. It's very important that we see this relationship.